Hello everyone. Today we will continue discussion on Quasi-Newton methods from lecture 7 onwards. Recall that these methods are motivated by the speed of Newton's method, which shows quadratic convergence when it converges. But in general, Newton's method does not always converge. So these quasi-Newton methods try to improve upon the Newton's method by making sure that the algorithm has better convergence and also has better speed, because in Newton's method we try to take an inverse of a matrix, which we would like to avoid as that is expensive. So let's recall the main steps. The Newton step is really minus of the inverse of the Hessian at the current point into the gradient at the current point. The problem with Newton's step is it is expensive to compute. Because of the inverse, and the step may not lead to an improvement in the objective function. So we may not descend if we take the Newton step. So as we discussed last time, these quasi-Newton methods try to overcome these difficulties. The general scheme is that at the kth iteration we pick a direction Sk similar to Newton's method, but we don't really use the Hessian inverse. We use the matrix H, which is positive definite, and this ensures that Sk is a direction of descent. And also we would like Hk to approximate G inverse, so that we get the nice convergence properties of Newton's method when when we are close to the solution. Once we have found the direction, then we can do line search, and this line search can be either exact, which is expensive, or inexact. Usually we do inexact, but for proving certain theorems or deriving some results, we may consider the case of exact line search as well. And the last step is to update Hk. So Hk plus 1 is equal to Hk plus something. And what we add here leads us to the type of the quasi-Newton method. So depending on whether this term is a rank 1 update we might get a different formula. If it's a rank to update, as we will see today, we can get many different formulae. And depending on what we choose, the method may or may not differ from others. And this continues until we converge. So so recall that gamma k, which we used to represent the difference between the gradients, is equal to the Hessian times the change in the coordinates of the points plus higher order terms. And this comes from Taylor series expansion of the gradient. If my function is quadratic, then these higher order terms are 0. So quadratic functions are actually a very nice test set for these methods, and you can prove some very nice results for just the quadratic functions, which can then motivate us to prove similar things for general nonlinear functions as well. So since we want to avoid computing GK and its inverse, we use a quasi-Newton method, quasi-Newton condition, which must be satisfied by these formulae or by these methods, and this is sort of the defining condition for these methods. It says that basically we just take G to the other side, so and do HK plus 1 equal to HK plus 1 into gamma k must be equal to delta k. So notice that even though in the earlier equation we had GK, here we have HK plus 1. And the reason we choose XK plus 1 and not HK has been explained in the previous lecture. So recall that for a rank 1 update of HK, if we want HK plus 1 to differ from HK by a rank 1 matrix only, that means a small change from HK, then there is only one update which is possible, which we saw last time, which satisfies this quasi-Newton condition that we talked about just now, and that is given by this formula: HK plus 1 is equal to H plus delta minus HV. I'm sorry, this is a gamma divided by delta minus H gamma transpose gamma. So as we discussed last time, this may not converge. The direction may not even be a descent direction, because the denominator might be negative and the whole thing might not give us a positive definite matrix. Also, it might have numerical difficulties. So this is almost always not used. Far more popular are the rank 2 updates. One of which we saw last time, that was the DFP formula. It says that hk plus 1 is equal to h plus product of deltas divided by scalar minus another rank 1 matrix divided by a scalar. So each of these two terms that we add to H are rank 1. So we get a rank 2 update for H. This method is named after David, Don, Fletcher and Powell. And it turned out to be pretty good and useful. And we saw this method and tried to derive why we should get this form. So related to H is the matrix B. So let B be H inverse. Okay. So recall from our earlier discussion that H inverse was used to model the Hessian of the function. So this B is sort of a proxy for G. So I can have a formula not just for H but also for B. And this is the exact inverse, not an approximation. I need an exact inverse for B. And with little bit of thought and cross-checking, you can verify that at least for DFP, we get 1 plus delta transpose B delta upon gamma delta gamma transpose by gamma delta minus gamma delta transpose B plus B delta gamma transpose So this looks far more complicated than the update formula for hk plus 1. Here B is the previous value of B in the previous iteration. So all subscripts have a K, which we have omitted for simplicity. So so one can verify that this is also rank 2 update, and not too difficult to compute. And one can also verify so first of all we can verify that these two matrices that we wrote are inverse of each other, and we can also verify that gamma k is equal to bk delta k, which is just the Quasi-Newton condition, but I have taken h to the other side, and its inverse is b. These are some things which are somewhat easier to verify. You just plug in the formulas and simplify, and you should be able to verify.